found one, the desired, right? But this one is not enough, right? We still have one minus C1n, right? Sorry, minus C2n. So that one goes here. 这样可以吗？了解吗？就是你两个加起来，你这两个加起来是一个字的。对，我们现在放入在这边，因为我们要满足这个上面这个。那还差这个，就是把它放在这个 minus 这个我所谓的 what I call residual, right? And then we just need to make sure the residual is greater than 0, greater or equal to 0. Then we have this write it down, get rid of that residual. PK 对，这个就是我们假设的format， 这个 format， 对，不管那个 k 是多少，都必须要跟这个 format 满足。所以当我们现在 induction 走多一步到 n 的时候，它也必须要像 C1n square minus C2n 所以这是为什么我们有这个东西。这样可以吗？因为这个我们希望这一块的 format 跟这一块一样。Okay, we need to make sure that it is consistent. Okay, so this is the desirable part and the residual. So just remember, here, remember, eventually, what you want to get is this one minus this one. Desired part, okay, when your assumption is easy, the desired part is easy, right? But when your assumption is a little bit complicated, the desired part will become a little bit complicated. I mean, it has to be the same as what you assumed. Okay, it has to be the same as what you assumed. But whatever remains is part of the residual. And the only thing you need to make sure is your constant assignment can make the residual greater or equal to 0. So that, in the following, okay, you can not write this part, just write the desired part. Okay, so that's the basic idea. Okay. Oh. Obviously, like I will, as I said earlier, I will assign like homework. I mean, to you like sometime before end of this weekend, before this weekend, and in the homework, you also need to practice. It's like substitution method. Okay. And obviously, like the difficult part, if you ask me, what would be the difficult part? I will tell you, the difficult part is how do you guess the right order, right? Yeah, because like all the other parts are kind of like logical, but the only thing that is a little bit like coming out of nowhere is if you guess the right order. But it depends on what we want, right? If you want a tight bond, obviously it may be difficult. But if you want like just big old notation, like not necessarily tight, a lot of time is easy. Okay? So it depends on what you want. Okay? 为什么？有问题吗 ？OK， 没问题，我就继续了。OK， So and also as I said, like another alternative is you can use like a recursion tree to help you guess a better like for this proof, for substitution method proof. Okay? So recursion tree. Recursion tree model, the cost or the time, okay, of a recursive execution of the algorithm. So recursion tree method can be unreliable, just like any method that use ellipse, because like I mean you can never use like da 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 for more proof. Okay, I mean why is the substitution method more powerful? Because it is grounded on induction. You don't see like a da 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 in the previous substitution method, right? But when you draw the induction tree, I mean you see that like ellipses. Okay, so that makes the recursion tree informal. That is why we say recursion tree cannot be used for proof. It can, but however, it can be used for intuition. Okay, it can help you to find a better bound, and then you can use a substitution method or other method to prove it, basically. Okay. So recurring tree method is good for generating guesses for substitution method, as I said earlier. Because the substitution method, how do you guess a good bound? That's the difficult part. So you have seen one example of recursion tree. Okay, I mean, which is like in merge sort discussion, right? In the merge sort discussion, we talk about recursion tree. Okay, and that is like a simple application recursion tree. So now, okay, let's have a look at a more complicated example. So this is like Tn equal to Tn divided by 4 plus Tn divided by 2 plus n squared. This is like a little bit more complicated, right? And this, if you ask me where does this recursion come from, it could come from like divide counter, it could come from, pretty much any possible like recursive algorithm. Yeah, it's but it is indeed argued. Okay, a little bit argued. So we can basically follow the recurrent tree we discussed in the previous chapter. Basically, this is Tn, and then you apply this recurrence relation, so the root becomes n cubed, also n squared, and you have like 2 branches, so it becomes like this, right? That is how recurrent tree looks like, and then you apply the same idea on both children. Okay, so the left side becomes n divided by 4 squared, and then you have like 2 more children. And the right hand side becomes like this, 2 more children. Right? Okay, and then, okay, you can, da 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 da. And here, we only write this branch. We only write this big theta 1 on this leftmost branch. Why? Because this is the branch that terminates the fastest, right? Because every time you go to the left-hand side, this argument gets divided by 4, right? Every time you go to the left hand side, n gets divided by 4. You go to the left hand side, n gets divided by 4, and so on. And for all the other branches, n is divided by something smaller than 4, right? At least at some point of time, right? So, you know, for a fixed n, okay, the leftmost branch will, you know, reach 1 the fastest, right? All the other branches will be deeper. Okay, the deepest one is the rightmost branch, obviously, right? Okay, but you don't need to draw them out completely. Okay, well, we can say that's the beauty of recursion tree, but that also results in this informal, make it informal. But anyway, well, let's take a 10 minutes break. When we come back, we'll continue the discussion. Okay?